Okay, this video presentation is going to be about solving systems of equations by using substitution. We're going to start with a short video clip that's going to work you through and kind of tie into the solving systems by graphing that we did previously and explain the substitution, and then we'll work through some examples together.
In this lesson, you are going to learn how to solve systems of equations algebraically by substitution when one equation is in slope-intercept form. Let's recall that a system of equations is two or more equations with the same variables. A system of linear equations, which we will be studying in this lesson, is when you have two or more linear equations with the same variable. There are three examples below. A solution to a system are values of x and y written as a coordinate point, xy, that satisfy each equation. You can always solve systems by graphing, but this is a difficult method to find exact solutions. We typically use algebraic methods to find exact solutions. There are two methods for solving systems algebraically: substitution and elimination. I am going to explain the idea of substitution by showing how you've substituted in your mathematical past. Here we have two problems where we've used substitutions previously. In the first problem, x squared plus 9, where x equals -8, I'm going to substitute -8 for x. So I'm just going to plug it in. And typically when we substitute, we put parentheses around what we're substituting. So I get -8 squared is positive 64 plus 9 equals 73. And the next problem, y equals 2x minus 4, where x is 3. Again, I know what x is. I'm going to substitute it in for x, 3 in for x. And I get y equals, well, 2x is the same as 2 times x, so 2 times 3 minus 4, again using parentheses. So in this case, y is 6 minus 4, or y equals 2. Let's see how this idea works in solving a system. Solve the following system by substitution. Y equals -3x plus 5, and 5x minus 4y equals -3. When you have an equation in slope-intercept form, y is by itself. Slope-intercept form, if you remember, is y equals mx plus b. So we know that y equals all this. Additionally, a system are two equations that work together, so the x and y values are the same. So if y equals all of this, I can substitute it in for the y below. And I'm going to substitute using parentheses as we did previously. So we have 5x minus 4, and instead of y, I'm going to put in our substitution, equals -3. Now, like in the previous examples, I am going to simplify and solve for the variable that I have. I'm going to use the distributive property here, so -4 times -3 is positive 12x, and -4 times 5 is -20, equals -3. 5x plus 12x is 17x minus 20 equals -3. Well, now I'm just solving an equation. Notice when I made my substitution step, I went from having two variables, x and y, to having only one variable. This allows us to actually solve the equation as we've done in the past. Now I'm going to use inverse operations. Add 20 to both sides. The 20's cancel. I get 17x equals 17. Divide by 17, again, inverse operations, and x equals 1. But we're not done, because we know that a solution to a system is of the form x, y. We already have x, now we need to find y. To find y, we can plug in x into either of these two equations. But notice, in this first equation, y is already by itself. So let's plug in x in our first equation. -3 times 1 plus 5. So y equals -3 plus 5, and y is 2. So it looks like our solution is 1, 2, 1, 2. Now, if you want to, we can actually substitute it in for the second equation. Let's just try it to show you that it works no matter what equation you use. Again, substitute 1 for x over here. 5 minus 4y equals -3. Subtract 5. negative 4y equals negative 8. Divide by negative 4, and y equals 2. So again, it doesn't matter where you plug in, it works for both of them. Finally, as a check step, you could graph both equations, and when you do that, the solution is the point of intersection. In this case, it is 1, 2. So our answer is 1, 2. So now you know how to solve systems of equations algebraically by substitution when one equation is in slope-intercept form.
Okay, so you can solve a system of equations using different methods. The idea is to determine which method is easiest for that particular problem. These notes are going to show you how to solve the system by using algebraically by using substitution. Recall that previously we were solving a system by graphing. This is a second way that we're going to show you how to solve them. So step 1, you need to make sure that one equation is solved for one variable. Sometimes it is easier to solve for y, sometimes it's easier to solve for x. I always try to pick the one that the coefficient of the variable is 1 so that I don't have to do any division. Or always look to see if one number is a factor of the other two, because if one coefficient is a factor of the other two numbers in the equation, then when you divide you will get even numbers. So we kind of saw an example in class when we picked the wrong variable and ended up working with some very messy fractions. So we have some choices that we're going to have to make. Sometimes fractions cannot be avoided. So we'll put the equation that we solved in step 1 into the other equation so that we can get an equation with one variable. We'll solve that equation, get the variable by itself and a solution, plug it back in to find the other variable, and then check your work. Okay, so let's solve this system using substitution. Note that one equation is already solved for y, and we can use that in the first equation. So we're going to solve an equation for one variable. The second equation is already solved for y, makes it a lot easier. We will substitute in to the original equation, and in place of the y, we will put the expression 3 plus x. Now we have an equation in one variable, and we will simplify. So 2x plus 3 equals 5. Subtract 3 from both sides to get 2x is equal to 2. Divide both sides by 2, and you will get x is equal to 1. Step 4, plug it back in to find the other variable. If x is equal to 1, 1 plus y equals 5, or y equals 4. Finally, check your solution. Double check that it is true for both equations. The solution 1, 4. What do you think the answer would be if you graphed the two equations? So if we graphed them, we should get the same thing. Okay. Which answer checks correctly? So in this case, remember they're ordered pairs, x, y. You could do some substitution and plug and chug and see which one works, or you could solve the system. We're going to go ahead and solve the system just to be sure. So since we can tell already that x is solved for this, we will substitute it in place of this one. So we will get 3 times 4y minus 17 minus y, just bring in the rest of the equation, will be equal to 4. Use the distributive property. So 12y, I need to do a little math here, minus 51 minus y equals 4. Combine like terms, so the 12y minus y will be 11y Then just solve for y by using an inverse operation. And finally, divide both sides by 11 to get y is equal to 5. If y is equal to 5, we can plug it into one of the equations. I'm going to choose to plug it in to the second equation. So x would be equal to 4 times 5 minus 17, or 20 minus 17, so x equals 3. And so if x is equal to 3 and y is equal to 5, that makes choice 3 the correct solution to this system. Let's solve this system using substitution. Now both equations are in standard form. Looking at all of them, the easiest one would be to solve the first equation for x because the coefficient is 1. So x will be equal to negative 3y plus 7. Now we can substitute that into the second equation. So in place of x, we will put negative 3y plus 7. We must do distributive property, so 4 times negative 3y and 4 times 7. So negative 12y plus 28 minus 2y equals 0. Combine like terms. A negative 12y plus a negative 2y will be negative 14y plus 28. Subtract 28 from both sides. Negative 14y is equal to negative 28, so divide both sides by negative 14. And y is equal to 2. Substitute that back in to find the other variable. So x will be equal to 1. Now check your solution. In the first equation, 6 plus 1 does equal 7. And in the second equation, 4 minus 4 does equal 0. So we know that it is correct. And then this question is posed: when is solving systems by substitution easier than doing the graphing? When only one of the equations has a variable already isolated, like in example 1. So sometimes you'll have a system and it'll already be solved for y or for x. If you solved the first equation for x, what would be substituted into the bottom equation? So let's solve the first equation for x. So we will subtract We will subtract 4y from both sides. These are not like terms. So we'll get 2x is equal to negative 4y plus 4. We will divide everything by 2. So if you do not have a variable whose coefficient is 1, always look for the equation that's easiest to work with, that has coefficients that maybe one coefficient is a factor of the other two. Notice that the coefficient of x is 2, and it is a factor of negative 4 and 4. So this will cancel. X will be equal to negative 2y plus 2, and that makes the second one the correct answer for what the expression will be when substituted, that we could substitute it into the second equation. And again, pay very close attention to your x and y variable. I think the biggest mistake that I always make is I turn one into the other. However, I did have it correct on the previous slide. Let's see if we can go back there. Yes, I did. So that would be negative 2y plus 2. Which is what it is. So sorry about that. I thought that I had boxed in the third choice, which I didn't. Okay, so let's solve this using substitution. So solve the equation for one variable. The first equation is already solved for x. Substitute it in. So we have 3 minus y plus y equals 7. Solve the equation. 3 is equal to 7. The variables in this case were eliminated. And this is a special case. Does 3 equal 7? And the answer is no. So since this results in a false answer, there are no solutions. So in case you were wanting to know, what does that mean about these two lines? It would mean that they are parallel lines and they have no solution. Let's solve for this system. The first equation is easiest to solve for y. So y is equal to negative 2x plus 4. Let's substitute that in. Simplify. And if 8 is equal to 8, this is true. And it's also a special case. What was the other special case that we had when we were solving by graphing? We had 3 possible choices. The lines were intersecting and they were solved for 1 point. The lines were parallel and there was no solution, or the lines were the same and they had infinitely many solutions. So when the result is true, the answer is infinitely many solutions. And I don't know if you recall when we had variables on both sides of the equation, we had situations that were very similar to this. What does it mean if the result is true? That they intersect, that they are parallel, they are coinciding, the lines reciprocate, or that I can spell my name. I hope you all chose 3, that they are coinciding, which means they are the same line.